we'll talk about flash and the semiconductor industry, and then if we still have time, we're going to talk about DRAM. So first, let's start with erasable programmable ROM. And it uses CHE technology. It's called channel hot electron. Channel hot electrons in this EEPROM memory. So it looks like this. Definitely 2 gates. So poly 2, poly 1. And poly 1 is performing as a floating gate over here. That's P1, that's P2. And you want to connect both the drain and poly 2 to the high voltage, for example, 25 volts. And ground here. So what's going to happen is, so this is for programming. When you're programming an EEPROM, it works this way. So you need a high voltage, 25 volts, for example, and it's going to open the channel because the voltage is high, even though there's an intermediate gate in the middle. But it's going to attract the electrons flowing in the channel, and some of the hot electrons will jump into poly 1 and being trapped there. So you can memorize that state. So that's for program. And we want to erase it. You have to use a ultraviolet laser or light to erase it. So this is kind of a old technology, not being used too much anymore right now. And the difference between this one and the modern flash is the oxide is thick. So you cannot erase it easily using electricity or any of the digital control systems. So here is the oxide, which is relatively thicker than the modern flash memory. So that's the old version. It's called EEPROM. And after that, engineers developed another one, which is called EEPROM. EEPROM. It's electrically erasable. And programmable ROM. And since it's programmable and also it's erasable just using electricity, so it's not ROM anymore. Right? You know it's called ROM, but it's not ROM anymore. It's not read only. You can also write it easily just by giving a higher voltage. And the mechanism behind the scene is not CHE anymore. It's called FNT. So what is FNT? It's Fowler, that's a person's name, Fowler Nade Nordheim, Nordheim. T stands for tunneling. Okay, so the way to program it and erase it is kind of different compared to EEPROM. For program, it's still a floating gate in here, P2, P1, but you have, this is too small. It's N plus, and you need a P well. It's a double well precise compared to the C5 we have learned. That's double wells. That's a P well and also N well in the substrate. Here's a P sub. And so what's making this different is, so in the P well, it's going to have a P plus connector. And in N well is here. So I shouldn't draw here, shouldn't draw this. So that's the N well. N well also has an N plus connector. Since we need a P well because we want to give a different voltage to the P well here, so that's why we have to insulate it from the P sub. If you do not have another intermediate N well here, it's going to short this P well to here. So you cannot adjust the voltage for this P well. Since we need a P well with a different voltage compared to 0, so all the P sub are shorted to the ground. And we need a P well with a different voltage instead of 0. So that's why we need an N well in the middle, so it's not being shorted to the P sub. Right? If you have a P well, P sub, nothing in the middle, it's shorting that P well to the P sub, to the ground. So you cannot adjust the voltage for the P well. I'm going to show you why do we need a different voltage for this P well. So for programming, you want to short the P well and N well to the ground. And you just need to apply a high voltage here. You want to short this drain to ground as well, but just a high voltage, for example, 20 volts. And it works differently compared to the CHE mechanism. What this guy doing is it's going to directly attract the electrons from the P well. It's going to move up to the channel and then tunnel to the P1 layer and being trapped over there. So you can change the state of the gate. You can memorize the state. You just need 2 states. One something different for binary. Right? You can convert this kind of 2 states to binary values, but now we just need to differentiate 2 different states. That's how the memory works in the binary system. So this one allows the electrons directly tunnel through the oxide and being trapped in P1. This one is different. This one is when the electrons are moving happily, freely in the channel, but boom, just directly jump into the P1 and being trapped there, right? So the electrons are not expecting to be trapped there, but just in case they are in there by chance. But these ones are not. These ones are super strong electric field. And the reason these guys can be trapped in here is because the oxide here is relatively thinner compared to this one. A lot thinner, actually. So that's why it can allow this kind of effect to happen. But it's not happening here because it's thick. This is thin. Can directly attract them to here. And you still need a high voltage to make this happen. Right? This is for programming, for erasing. For erasing. Still need 2 gates, P2, P1, and either N plus, and you need still the same transistor, it's not changing the transistor. That's a P well, and here's the N well. Definitely you need an N plus as a connector or contact to this N well. You need a little bit heavily doped N plus material over here. So for erasing, what this guy doing is, no, here's a P plus. Just directly connect this tool to a high voltage, 20 volts. So it is able to attract all the electrons being trapped here to the ground. So all the electrons here will be moved back to the well, and then they will go back to the ground through this 20 volts power supply. So these channels, drain sources are not engaged in this event. So they are directly being attracted to the ground by this 20 volts high voltage power supply in the wells. So it's happening in the wells, not in the channel. So don't actually need the channels. What you want to do is just float it. Or ground it. I think you need to ground it to float it. Let me double check. Yeah, floated actually. You just need to float. Since you are grounding these ones, here's the source, ground it. Since when you ground it, you got more. If you ground it, it's actually being shorted to here and shorted to any of the power sources. So you get more places to source electrons. So this can happen relatively faster. But whenever you are trying to erase the trapped electrons over here, you don't want to source anything somewhere else. You just need a high voltage power supply, and then directly just remove all the electrons from here, and then you're done. You don't want to short them to the ground. You just float them, but just ground this guy, so you can form a loop. So that's program that's erase of this EEPROM. And since you can do it really quickly, and that's why we call it flash, it's being used anywhere in the industry, in the microcontrollers, in your smartphones, you know. So you can program it, and it's going to store there. It's non-volatile. It's going to stay there for a long time. So that's program, that's erase, and there's another state. It's called do not program, because sometimes it's programming all the flash page by page, and some of the cells you want to program it, and some of the cells you don't want to program it. How can you make that happen? Because whenever the one gate is being connected to 20 volts, it seems like everything will be programmed at the same time, but you can control it actually. So what's going to happen is, if you have something being shorted to the same gate, right? If you ground the drain and source, it's going to program this gate, this floating gate. But however, if not, for example, if you have something like this, so it's totally controllable. P plus, because it's a P well, and N well, you need N plus as a contact. Of course, when you're programming it, these two are definitely grounded. But when you provide a 5 volts, it's not 20 volts. So you compare these two, what's the difference? So for this one, when you are trying to program the flash for just this NMOS cell, memory cell, you ground the drain and source, and give a high voltage to the gate. For this one, this is do not program, resist to be programmed. You just give a little bit voltage to the drain and source at the same time. Then I think what's happening is that when the electrons are being trying to be attracted to the P1, instead they are going to the 5 volts. So the electrons cannot get into here. Okay. So this is not programmed. So if you have the same page, page means the same row of all these cells. For example, something like this. For example, these are all the flash. You have 2 gates. That's how you draw the symbol. The floating gate. That's one page. One page of flash. There can be many other ones. Right? So if you give the gate a 20 volts, so all of them will be programmed if you give 0 volts to the drain and source. Right? So how can control that? You can control each one. If you give 5, it's normally these are the bit lines. So if you have like 5, 0, 5, you don't need 2 5s, you just need 1 5, so the electrons will just go away, not going to P1. So these are the bit lines, bit 0, bit 1, bit 2. So when you are writing into a memory cell, what you are going to do is just give a 505. It's like a command. So you can control which one can be programmed, which one is not. Right? Since you have 5 volts here, 0 volts here, 5 volts here. So which one is programmed, which one is not? The middle one is programmed. So these two are not. Okay, so we got a memory cell, which is whatever, depends on your sensing circuit. So that's how you write and erase and do not program a flash cell. This is how you operate it. And there are more operations like read and write, so we can look into that really quick. No, there are more rows. You need more cells, right? You need just more. This is just one row, one page. You need more pages. Yeah, and this is called NAND flash. And I think Taylor just was in one of the interview for Intel and talking about NAND gate flash. I don't know if they are involved. So any of the NAND gate transistor level memory design are involved in that project. But why it's called NAND flash? There's no NAND gate at all. It's just because you have so many transistors in one string. When you are trying to read any of the pages, all of the transistors has to be on in order to get a current flow into it. So I'm going to draw the circuit really quick, because everything are in series, like the NAND gate transistor have drawn, right? So all of them has to be on in order to draw a current to the ground. That's why it's called NAND flash. So Samsung, SK Hynix, Micron, all these main players on the market are making NAND flash memory cells. The USB drives, for the microcontrollers, for anything being used in the CPUs. This is really popular, very, very popular. This is because all the devices you have right now, they are using NAND flash memories. Let's do the circuit really quick so you know what's going on inside. Why does this work? Why the NAND logic works for this topology? That's very interesting. So the cells, I'm going to draw the circuit real quick. 1, 2, 3, 4, 5. Let's see here. So there will be many other ones. So these are the source. Here's a P plus connector. Here's the N plus connector. And these are the two select transistors. And these are the memory cells with the floating gate. There can be more. It's not just 4, right? I'm just drawing 4 here. And all these ones are shorted together, so for all the gate. And these are being shorted to the bit lines. That's bit 0. That's bit 1. Let's just call it bit 2. So this is called select top. Just providing a switch so you can control the connection between the bit line and also the memory cells. And also you can have another one here at the bottom. So we can short it here, but it's not necessary to be short to the P plus. Select bottom. These are the word lines because they are the row selectors. The word 0, word 1, word 2, word 3. And these are the memory cells. And for each row, that's a page. So when you are either writing or reading from the memory cells, they are doing page by page. So that's page 0, page 1, page 2, page 3. let's think about it, how we write it, how we do a writing operation. So to do a write operation, let me do a table to make it clear. We're not messing up with a circuit. So table, I need 4 columns and the Bitline, select top, word 0, word 1, word 2, word 3, and select the bottom and N plus of the source of this transistor, and P plus of the P plus well. It's tied down to whatever, can be a ground, can be the 20 volts, depends on the operation purpose. And for different operations, erase, program, and read. So let's take a look at this, see what are the voltages we want to apply to these pins. Okay, let's do erase first. I want to erase. Based on what we just talked about over here, when we're doing the erasing operation, for erase, what do we want to do? We want to ground here and float these two. However, the electrons will be attracted to the P plus and N plus over here, right? So I have a 20 volts for the wells. That's how I erase it. For programming, you need 20 volts and 0, 0, 0. So I have many places to source electrons. And we still need something else because sometimes we don't want to program some of the cells. Whenever we're programming one of them, but we want to keep all the other ones not programmed. You can give 2 5 volts. You can give just 1, and then it's gonna keep this from being programmed. All right, memorize this 3 states. This is erasing, programming, and do not program. Okay. Now, let's look at this. That's a flash memory cell. And I want to erase it. I want to erase it. So what's the bit line should be? I want to erase whatever in there. It's just like refreshing, right? So anything stored in here should be erased from the while. And the while is not being drawn in this symbol, right? The symbol only has a gate, has a drain, and a source. It's not showing the whiles. So you can just think about there's another channel here at the bottom. It's going to transfer all the electrons to here. So in that case, you do need, you don't want to source too many electrons. So just keep this float. And you want to turn this on. So select top should be on. And, so select top should be grounded. So because you don't want to turn this on, you don't want to turn these on. It just ground all these ones. So it's not sourcing electrons to somewhere else. It just apply a high voltage to here is performing as this. So just connect the wells to 20 volts. So all the electrons will be transferred to the wells, to the ground through the wells. And you don't need to connect the gate to anywhere else, just ground it. And you are floating these ones. But all these ones are gates. So these are gates. So just ground them. And ground it. This should be float, because that's the source. Right. For programming, so what I'm going to do is, for example, I'm trying to program word 0. I'm trying to program word 0. So definitely word 0 should be 20 volts. Okay. And since I need to source electrons, I'm going to turn on the select the top. Turn on select the top. So you can give 5 volts or higher voltage to there. But normally we use a little bit higher voltage. There are not too many other voltages available. We just use 20 volts. So you can pass the entire 5 volts. If this is 5 volts, you can totally pass the 5 volts to the following transistors. But when you are programming, you need the 0 volts. See? When you're programming, you need the 0 volts. You need to ground the screen and source. So that's why the bit line need to be grounded. Because when you ground here or here, it's going to transfer that 0 volts to here. So you are grounding the drain. Okay, so you're programming this guy. But for all the other ones, you just keep it on. So give 5 volts, all of them. It's not just the sourcing electrons from the well, but also you are opening up the channels, so you get more places to source the electrons. So 5 volts will turn on these transistors, but it's not programmed. It's not high enough to tunnel these electrons to the P1 layer. But it's turn on the electron channel for the NMOSes. So 5 volts, 5 volts. Select the bottom should be also 5 volts, and N plus source should be 0 volts. So you have loop. You can close the loop, so you have places to source the electrons. That's how program it. For reading, since you are reading from the bit lines, from these bit lines, you definitely don't have to assign any voltages to it. So it can be high, it can be low, depends on the state you're reading from it. And when you are reading, do you need to turn on this or turn off this? You definitely need to turn it on because you need the current to flow through it. I'm going to show you how that works. So let's just find out the voltages first. For example, you are trying to read this row. Read from this row. And what you want to do is actually give a 0 volts. I'm going to tell you why really quick. Don't get bored. Okay. But for the other ones, just keep it on. I'll let you know why. This is the main thing. That's why it's called non-flash. Okay. Just keep all this on. Also this, keep this on. And 0 volts, 0 volts. So have a place to draw all the current to the ground. Just directly draw it to the ground. Since you ground it, the current is going to flow through here to here. So why we need a 0 volts to read in order to read this page? Since I just mentioned, when we are doing either reading and writing operation, we are doing page by page. So now we are talking about reading. We're reading this page. And we need to give a 0 volts to it. Because after you have programmed the flash cell, the ones has been programmed will have a higher threshold voltage. So that's VGS, that's IDS. This can be like 3 volts or something. And this is a negative threshold voltage for the programmed ones. I don't know if this is difficult to understand. So why, for the floating gate technology, whenever you get electrons being trapped in P1, Is the threshold voltage getting higher or lower? To turn on this transistor. So the gate voltage is not directly shorted to the to P1 as usual. It's being shorted to P2. So there's an intermediate layer in the middle, which is a floating gate, which traps all the charges, electrons inside. So whenever it's being programmed, you got electrons in the middle. And are the electrons increasing the VTH or decreasing the VTH? Decreasing or increasing? So the way to turn on the channel is to invert it, right? So you need a positive voltage to invert the channel so you can turn it on. But now what's happening is you got something trying to negate the effort of the positive voltage. So whenever you are making it more positive, but unfortunately the electrons are trying to negate it back. So that's why you need a higher positive voltage to turn it on, right? It's not, so you are trying to inverting the channel, not inverting the P1. The P1 is not doing the same effort as the positive voltage. It's like whenever you use this positive voltage to attract the electrons, and this negative voltage, this negative charge will expel electrons from the channel. So it actually moving the threshold voltage further to here. It's moving the threshold voltage to here. So what's happening for the negative threshold voltage? What's happening to these guys? So this is programmed, right? These ones are erased. So whenever it's being erased, it's not a Superman. So whenever you are erasing the electrons, there will be some extra electrons being removed from the P1, which will give you a little bit positive charge. So you don't have to give a pretty high voltage to turn on the gate. These are some positive charges. It's trying to help you to turn it on. So that's why you don't need anything and it's already on all the times. So when you are erasing it, what's happening is there will be some positive charges in the floating gate to keep the channel on. So if you have positive charges in here, then, for example, this has been programmed, right? This has been programmed, and now I'm trying to read this page. I just give a 0 volts to this row, and when I'm reading, keep in mind, when I'm reading, should I turn on these transistors or turn them off? When I'm reading, I'm trying to read this line. You can read line by line, right? Just using a decoder, just activate this one. So you are reading this line. So whenever you get the data being transferred to the bit lines, you know this is from this row. Okay. So now I'm reading this row. I'm turning on this one. How to turn it on? Just give a 0 volts. Why? Yes. So but in the same time, when you are trying to read this line, do you want to keep these lines 5 volts or 0 volts or 20 volts? Just think about it. I don't want to just directly write down all the numbers in the table and it's not making sense. I'm just trying to think about this intuitively so you understand it. So I'm trying to read it, right? I want to give a 0 volts to here. And do I want to give 5 volts to these lines, the other lines, or do I want to give a 0 volts? Or do I want to give 20 volts? So definitely not 20 volts since you are programming the cells, right? You are reading, not writing. Definitely not 20 volts. So it's either 0 volts or 5 volts. So give me an answer. Why and why? So why? It depends on the page of the rating. So if you give 0 volts and 5 volts here, 5 volts here, 5 volts here, So look at this one. For example, this has been programmed. This is not programmed. This is not programmed. So they have different threshold voltages. Okay, if I give a 0 volts, will this be on or off? This is programmed. So programmed means it has electrons trapped in P1. Not programmed means it's been erased in the previous cycle. It has positive charges in P1. So programmed, then you have the threshold voltage being moved to 3 volts. It's relatively higher voltage. And 0 volts cannot turn it on. So it's going to block the entire string. That's why it's a NAND gate. It's a NAND logic. You keep all the other ones on, and you are trying to sense the current. So you can have a little sensing circuit at the bitline when you are reading it. So whenever it's trying to draw current from whatever here, right? Whatever you are having here is a sensing current, can be a current mirror. And you can sense that current flow through the channel to the ground because this is on or off, I don't know. So is this on or off for this case? For programmed cell, I've given 0 volts. Look at this one. It's programmed, 0 volts. Is this one on or off? Look at this curve. This one, 0 volts, on or off? Off, right? Are you getting any current from here? No, so there's nothing for the sensing current, sensing circuit. It's not sensing any current. So you can tell, hey, this has been programmed. So you can tell the difference between two states, programmed or not programmed. You only have 2 states in binary, right? You can convert it into one, you can invert it to whatever, but you can define is this a 1 or 0 by yourself. Although this one is not programmed, which means it has been erased at some moment in the past. So what's the threshold voltage? Negative. If you give it 0 volts, it's going to turn on this transistor, and it's going to source current from the sensing circuit. You're getting a current flow into the string, right? So you can tell, hey, this is a different state. So you can define whatever. It can be 1, 0, 0 or 0, 1, 1. Doesn't matter. So get a memory cell. It's memorizing the state by using the floating gate. Okay, so it's not a cap like DRAM. It's not like a positive feedback like SRAM. So the DRAM and SRAM both need power supply. So that's why they are volatile. For this one, it doesn't need a power supply. So does this need a power supply or not? When you program it, definitely, right? So when you're programming Arduino, you need a power supply. And when you are plugging your USB drive into the computer, definitely your laptop has a LiPo battery. It's going to charge up the USB circuit, the memory cells, the flash cells in there to get power. So you can change all the states and memorize it. So the charges will stay there for a long time. You know, I don't know how long, but super long, right? Your USB drive, you are not losing the data normally, right? After 30, 50 years, still there. The charges will stay there. And so it's non-volatile. Flash is non-volatile. SRAM, DRAM are volatile, right? That's how I read it. So when you write it, you need the program, right? Is writing. You give, for example, we are still writing here, writing to here, and you give 20 volts to here, but 5 volts to all the other ones, so you can turn on the channel. You got more space to source electrons. Give 20 volts to this page, and program or not program depends on what? The bit line. Where to look at it? here. The ones has a 5 volts is not being programmed. The ones has all grounds are being programmed. Auto control it. For example, 0, 5, 0. So which one is programmed, which one is not? For writing. These are being programmed. This one is not. Okay. Because of this. So you have full control of everything. Program, not program, erase, read. Okay. And do you understand why it's called NAND? Because all of them has to be turned on in order to source the current from the sensing circuit. We don't have the sensing circuit, but there will be current flow through it. You definitely have a way to sense that current. Right? That's why we are electrical engineers. You have to find a way to sense it. It can be a lot of others, all the other options. So after taking this class, we are not designing the sensing circuit, but whenever you are going to do this, if you are working for a company like this, they can understand this really quickly. All right. Probably not, since the devices are not, they don't have the floating gate. It only has one gate. I don't think there is a, you can do it in electric VLSI, but I think you probably have to think about how to design the schematic yourself. You can definitely just directly hand draw the layout yourself. Just think about it. Just grab a standard NMOS and grab a poly tool and place the poly tool on the top of poly 1. Right? You can modify it because that's a physical layout. You can draw whatever you want. You can draw a device. However, in the schematic, when you're doing LVS, you probably have to think about how to do it. If there's a device, I don't know, just look at the library. There might be a device that has two gates, as a floating gate, so you can do LVS. There's no problem to draw it and fabricate it. The problem is whenever your circuit is being scaled up, and if you cannot do LVS, you just don't want to spend the money to fabricate it, right? You have thousands or millions of wires, and any wire can screw up everything, and you're spending like hundreds of thousands of dollars to fabricate the chips, and cannot do LVS. You don't want to fabricate it. Okay. All right. Okay, let's cover something about the semiconductor industry, which will be included into the final exam. So I want you guys to temporarily memorize it. If it's just for a few days, it's still better than nothing. Still better than not doing anything. So all the different sectors in the semiconductor industry, some of them you have heard about, some of them you haven't heard about in the past, but they have different roles. It's an ecosystem. So we're going to start with the semiconductor foundry. Okay. TSMC, Samsung, SK Hynix. And there are service company like Moses or Muse, all these companies. They will contact different customers and collect all the designs on one wafer, because the wafer is kind of huge. Every single design compared to the size of the wafer is tiny. So it's not making sense like one customer only want to prototype about 10 dies and you want to directly use one wafer for the fabrication. So normally these companies will collect all the different designs, so you can send it to the foundry at one time, so you can reduce the cost. That's how we fabricate our chip 2 years ago with the analog circuit design with C5 with no cost. And then the EDA company, Cadence, Synopsys, Mentor, all these EDA design tools. And there's another one which is special, standard cell IP vendor, like ARM. It's a British company. So they will, so the fabless, or IDM, integrated device manufacturer, will collect, will use EDA to design their microcontrollers, will directly buy the IP cores for their CPU, for their microcontrollers. They can directly buy it. IP core, they don't need to mess up with anything inside. Just buy it with all the input and outputs. Just connect their logic circuits to the ports. You can see the ports in there. It's like a black box, like the symbols you created for your cells. So you can buy it. ARM, right? So definitely they will contact these companies whenever they get a design. They verified everything on PGAs. They will contact these companies to fabricate their chips. And if they have a huge amount of it's already commercialized, they want to probably have billions of chips to be manufactured. They can directly connect the foundry to do it. So these guys are making a lot of profit. And also, smartphone, laptop manufacturers, all these different manufacturers. So they are selling products. So what they do is actually R&D, packaging, manufacturing, distribution, testing, all this kind of works. So these companies will sell all these products to the public. So what are these companies? Kingston, making the DRAMs, and who else? What's the laptop company? HP. Dell. LG. LG probably has some fabless. So that's the semiconductor industry. I'm going to give you some examples about these companies. Who are they? But definition goes first. Fabless. So these companies do not manufacture semiconductors. They do not have foundries. So the typical companies include Qualcomm, NVIDIA, AMD. IDM is integrated device manufacturer. Include, who are they? Intel. So they have design teams, and they also have foundries. So no foundries. These ones have foundries. Intel, TI, Micron, all these companies have foundries. Samsung. So examples for fabless ones. And their revenue, just want to give you a concept on that. Country, company, for example, Broadcom, Qualcomm, NVIDIA, MediaTek, AMD. Countries, US, 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 Taiwan. And revenue from high to low, I don't know which year, but recent year, one of the recent years. Million.